problem 44, a double star. All right, so the car is going to go around this circle. Remember, as it's going around the circle, at any given instant, the force applied, the total force applied, has to be applied toward the center and has to be equal to mv squared over r. Okay? Now, depending on where we are in the circle, some of that force might come from gravity, some of it might come from the normal force of the track exerted against the car. So what we're doing is, it's saying we're taking the car at the top and we're saying that it's just barely maintaining contact. All right? So the total amount of force is going to be, as I said, some combination of the normal force and gravity. But here, this total amount of force still has to be mv squared over r. That is not a straight vector or a strector. It's wow, that's not much better. All right, so the force is straight down towards the center. It's supplied by gravity and the normal force. But if the car is just barely keeping contact, the car is just to remain in contact, we're going to solve for the point at which it's just losing contact. It's touching, but it's not touching, you know what I mean? We do that all the time, that sort of intermediate, that threshold condition, all right? So in other words, what is the normal force up here? Yes, that's what we're solving for, when the normal force is 0, okay? So all of the centripetal force is coming from its weight, okay? So we'll draw a free body diagram just to make sure we understand what's going on. But here, it's mg acting downward, and normal force is equal to 0. And that mg has to be equal to mv squared over r because it's moving in a circle. It's instantaneous velocity. Okay? So now, we could look at a more general expression. Anywhere along the circle, let's take right here, you have mg acting downward, and you have the normal force acting in this direction. Okay? But in this particular case, and so that means you're going to have a component of gravity that's radial, and I'll make gravity green here. We're going to have a component of gravity that's radial or centripetal, right, and one that is tangential. So if the car's moving in this direction, by the way, what's happening to its speed? It is slowing down, right? We've got this vector right here that's anti-parallel, okay? But that makes sense. Wouldn't you expect a car as it goes around to slow down a little bit? So we have a combination of, we break the vector down into those two perpendicular components. So we know that mg has got to be equal to mv squared over r. Okay? All right, so the car is given an initial speed of 4 meters per second. What's the largest value that the radius r can have if the car is to remain in contact with the circular track? All right, so what we have is a car that is at, oh, now look what you've done. All right, here we go. All right, so the car is right here at level h equals 0. We're going to take this to be 0 potential energy. It has a velocity, what was it, 4 meters per second? All right, so velocity is here. We got potential energy equals 0. We got kinetic energy is equal to 1/2 mv0 squared. Okay, so that is our energy budget. Okay, you've heard me talk about that before. That means that the total amount of energy that the car has throughout this entire thing is going to be equal to the sum of these two, which will just be 1/2 mv0 squared. Okay? Why is that true? What are the forces that are acting on the car while it goes around, while it goes here and then around the loop and goes out this way? What are the forces acting on it? Gravity and normal force, but the normal force is perpendicular. So the only thing that's doing work on the car is gravity. Gravity is a conservative force. That means we know that energy will be conserved. Okay? That's what this is right here. So we know, now we're going to go out here. All right? So now we know at the top of the circle, what is its height? 2r. Good. All right. 2r. It's its diameter. So height here is equal to 2r. Got it? So at 2r, we know that its total energy, 1/2 mv squared plus mgh, which is 2r up at the top here, okay? That amount of energy right there has to be equal to what? This energy down here, okay? Because energy is conserved. Now we just set those two things equal to each other, and we could say 1/2 mv naught squared is equal to mg 2r, because that's the height. And what is this again? This is its what? Potential energy. All right? Plus 1/2 mv at the top squared. But now we're going, wait a minute, what do we know about v at the top? How do we don't know what that is? Well, we can find that based, oh wait, but this we don't know, and this we don't know, do we? But which one of those have we already partially solved for? I'll give you a hint. It's circled in blue. Okay? And so what does that mean? We know that v squared is going to be equal to, what is it going to be? GR, right. V squared is just GR. Okay? V squared. And we didn't bother taking the square root and then squaring it again. It's just V squared. So we know that 1/2 mv naught squared is equal to mg2, and I'm doing the r in a different color because that's what we're trying to keep track of, right? That's what we're solving for, plus 1/2 m, instead of v squared, we're substituting gr. All right? Nope, that's not squared, because remember it was v squared that's equal to gr. Okay, so that's our straight substitution. Yes, we do want our R in blue, both the first one and the last one. Thank you, Nate. All right, so what else is convenient here? Cancel the M's. All right, so now we got a bunch of stuff here. So we're going to have to gather our R's here to gather our R's. We got 1/2 v naught squared is equal to R times the quantity 2g plus 1/2 g. No way. Look at all those G's. G, it's like G, no. It's 2.5 G, not 6 G. G6. All right, so we got, so now what we got to do is divide through by this right here, right? So R is equal to V naught squared over 2 times the quantity 5/2 G. How's that for cool? All right, so R is equal to, thanks, Sam. Or is that, okay, what's there? All right, so V naught squared over 5G. How about that? So what are we given? V naught was 4 meters per second. 4 meters per second, entire quantity squared there, divided by 5G, which is 49 meters per second squared. So we got 16 49s, right? R is equal to 16 meters squared per second squared divided by 49 meters per second squared. Dimensionally, what happens here? Meters, right? So what's 16 over 49? Calculator. 0.33. Third, yeah, because it's actually a little bit more, because that'd be 16/48. So it's 0.33 plus a little bit, and the answer is meters. All right? Boxing.